All right, let's talk electron diagrams, aka orbital diagrams. So, first, what does that mean? Consider, for example, titanium. Let me find that on here. Here's its electron configuration. I'm assuming you, the viewer, have already figured out electron configurations. You should do that first before attempting orbital diagrams. This is the proper electron configuration, but it only contains some of the information. There's further information not shown here in terms of the orientation of the electrons. So essentially, an electron diagram or an orbital diagram is taking this and representing it as a picture. Notice your 1s2, each of these arrows is an electron, so there's your 1s orbital with 2 electrons, 2s orbital with 2 electrons, 2p orbital with 6 electrons, 2, 4, 6. Your d orbitals can hold up to 10 electrons, so notice there's enough boxes here to hold 10 electrons if you got 5 boxes with 2 electrons each. So, okay, notice how this is essentially taking this diagram, or sorry, this is taking the configuration and representing it as a picture. So if you can do the configurations, you can do the diagrams. It's just what these do is give extra information about the way the electrons are oriented, and therefore it can tell you things about like its magnetic properties and such. Okay, here's how you actually come up with these. And I'll go through some of these, kind of how it works. Hydrogen. Its configuration is 1s1. So the way you draw the diagram is you label 1s and you put an arrow. It doesn't matter if it's up or down, honestly. I just happen to choose up just because. Helium. You should be able to come up with, using the periodic table, its electron configuration is 1s2. So the way you draw that, box with a 1s label, that way I know it looks like a 15, but 1s, well, maybe I'll do that. Maybe it looks like an S. I don't know. But you put 2 electrons in there, showing that they're spinning in opposite directions. The bigger the configuration, the more boxes you need. Boron, 1s2, 2s2, 2p1. So there's your 1s. Here's your 2s. There's your 2p. 1s2, 2s2, 2p1. So, Pauli exclusion principle. You can't put more than 2 electrons per box, and they must have opposite spins. So there you go. There's your opposite spins, no more than 2 electrons per box. Hund's rule. Well, we'll get to that next. Aufbau principle, you start from the bottom and fill it as you go toward higher energy levels. Now, Hund's rule applies when you see carbon. 1s2, 2s2, 2p6. Whoops, 2p2. Whoopsies. Okay, make that clearer too. So there's your 1s, there's your 2s, there's your 2p. So 1s2, 2s2, 2p2. So there's one of the electrons for the p orbital, but you're not going to pair them up. You spread them out like this. That's Hund's rule. You don't pair them up until you have to. Okay, and let's see. If I had 1 more, it would go here. If I had 2 more, then I'd put one of those 2 here, and I'd have to pair the other one up. So what's got 2 more electrons than carbon? That would be oxygen. 1s2, 2s2, 2p4. So there's your 1s, there's your 2s, there's your 2p. 1s2, 2s2, 2p, 1, 2, 3, 4. That represents an upward facing arrow right there. There's your downward facing arrow. I realize I just made a little bit of a mess here with not drawing the box very carefully, but hopefully one gets the idea. Okay. So the bigger the atom is, it doesn't matter. If you can do the configuration, you can do this. So let's do, I did titanium in the notes, so I guess you can do that. Let's do cobalt just because. And look at the periodic table and use that to get cobalt as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. Okay. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Oh no, I'm out of space. So I guess I'll continue it down here because I just don't have a choice. Oops, not big enough. There we go. So this is only here because I ran out of space. Theoretically, it should be in line with the rest of these. It's just an oopsies. So that's what I would do. I've got the 3s, so let's see, 1s2. There's my arrows, 2s2, 2p6. I'm filling in all the arrows. 3s2, 3p6, 4s2, 3d7, 1, 2, 3, 4, 5, 6, 7. Following Hund's rule, I don't pair any until I have to. So that's your cobalt electron diagram. Now, last thing I deal with electron diagrams, what if you have an ion? So let's say, let's see, diagrams for ions. Start simple. Suppose you have, let's say, oxide ion. So oxygen would normally be 1s2, 2s2, 2p4. Remember, oxide ion's a 2 minus, so you add 2 electrons to this. So oxygen 2 minus is 1s2, 2s2, 2p6. So here's what you would do. So for oxygen, you do there's your 1s, there's your 2s, there's your 2p, 1s, 2s, 2p. Fill in all your electrons. But because it's charged, you need to do one extra thing. Add brackets and a 2 minus charge. This is how you do an electron diagram or orbital diagram for an ion. You do the same thing if it's got a charge. Even lowly hydrogen with 1s0. You would literally write 1s, leave it blank, brackets, and a charge. Because hydrogen is a hydrogen ion, if it's a positive ion. So what do you do if it's big? Same thing. Let's do a tricky one though. So the big ones, like if you're doing like copper or, well, arsenic or bromide or iodide, whatever, you do the exact same thing. You just do the configuration, the diagram, and you would add or subtract the correct number of electrons. There's no surprises there. There is a surprise when you deal with the transition metals. So the last bit is to deal with transition metal surprises. And I will do iron. And let's do iron as a 3+ ion. So for regular iron, that's 1s2, 2s2, let me see, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. 2p6, 3s2, 3p6, 4s2, 3d6. That's neutral iron. So iron with a 3 plus is 3 electrons less. Okay, here's the kicker. If you're going to take electrons out of iron, they come out of the highest numbered orbital first. So they don't come out of here first, they come out of here first. So I take out, remove these first, then remove these next. So for iron with a 3 plus charge, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Yes, that's right. When it ionizes, it comes out of here first. And then I took 2 out of here and 1 out of here in order to make it a 3 plus. What if it was iron with just a 1 plus charge? Well, that would have been, okay, here's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, let's see, 6. That's the original, that's just iron. For iron 1 plus, subtract 1 electron from here first. So I change this configuration. So that's a 1. That's right. The electrons come out of here first and then out of here once you're done taking them, once there's no more to take out of here. That's just the way it works. It comes out of the highest energy level first, the highest numbered energy level first, for whatever reason. All right, so any of the rest of these is going to be the same thing. Now, if you have a bigger one like this, for example, I guess, all right, sure, let's do a selenide ion, which, as you can see from its position, selenide is a 2 minus. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p. Let's do neutral selenium first. So I'm going to say selenium 4p1234. The ion, selenide, is same except 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. You just subtract off of here. 4p6. Sorry, I don't know why I just said subtract earlier. You add on to here if it's a negative ion, because in order to make it negative, you add electrons. So add 2 more electrons to make it 6 electrons. And then you would make the appropriate diagram for these. So I know all this time I've talked about the configurations. I haven't done the diagram. That's on purpose because the diagram can't be understood without doing the configurations first. So this diagram would be exact as you'd expect. A box here, 3 boxes, 1 box, 3 boxes, 1 box, 5 boxes, 3 boxes, etc. Here, how would this one look? For your iron plus, let's take that as an example. There's your 1s. That's your 2s. That's your 2p. 3s. 3p. 4s. 3d. So let's do the iron plus ion. There's your 1s2, 2s2, 2p6, 4s1, 3d6, 1, 2, 3, 4, 5, 6. That's what it would look like. Had you been doing the iron 3+, this box would be empty, and you would remove this electron right here. And it goes on more or less in that sort of fashion. So that should be a pretty good starting place, and that should get you a good start. Happy studies.